So here's an example of a recursive definition. So you have this set S that we want to define. And we have a basis step as usual. So we know that 3 belongs to S. That element is definitely there. And then we have a rule for generating new elements of this set based on what's already in the set. Well, what's already in the set? Basis step gave us just one element, and now the recursive step will generate a new one. Let's say if we only had 1 and we applied the recursive step once, what would we get? Well, we have 3 in the set. Okay, so let's take another replica of 3, because the recursive step tells me that if I have 2 elements that belong to S, then their sum is also in S. So apparently 3 plus 3 is in S. So now I have, after the first application of the recursive step, we have that 3 and 6 are elements that both belong to S. Okay, so the basis step together with one application of the recursive step gave me this result. 3 and 6 are in S. Well, I apply the recursive definition one more time, the recursive step rather, one more time. And now that I know that I have these 2 elements in S, okay, from this, it follows that 3 plus 6 is in S. Okay, 9 is in S. Okay, 3 plus 3 is also in S, but 3 plus 3 is 6, and that I already know to be in S. 6 plus 3 is also in S, the recursive definition tells me, but I know that to be 9, so I already knew that 9 was there, and so on. 6 plus 6 is in S, okay? Okay, so apparently 12 is also in S. So now I've expanded my set of elements that belong to S, so now I know that not only 3 and 6 belong to S, but after another application of this recursive step, I know that 3, 6, 9, and 12 also belong to S, and maybe there are other elements that belong to S. So once you've generated a few elements, the point is, you now begin to suspect that maybe all of the elements that are generated by this rule are multiples of 3. But it's one thing to suspect and have a hunch and intuition, and another thing to prove it. Well, we're going to have to prove it, and we'll use induction to prove this. Okay, so here's the statement that I'd like to prove. Okay, this is our statement. Okay, so let's copy that here. Okay, we'll call this a theorem. Okay, and now let's start proving it. Theorem. Proof. We do need the definition as well, so let me copy that so you have something to refer to as we carry out the proof. Okay, there's the definition up there somewhere. This is how S is defined. Okay, now we're going to prove facts about S. So here's the theorem that we're about to prove. Okay, so how do you prove something like that? So first of all, you start by being more concrete, by giving names to things. So give this set name a D. Let's call it A. Let's set A be the set of all multiples of 3. So this is the set of integers, set of all multiples of 3. Multiples, and I'm going to write this in detail, this proof in detail, so you can ask me questions in every step if there's something unclear. Of all multiples of 3. Here's what we want to prove. So the theorem says that S and A are one and the same set. Okay, so we need to show that A, all multiples of 3, and S are the same set. So just to be clear, maybe that's extra, but let's write it down anyway. So these are mults of 3, 2 sets, completely different sets, different definitions of the sets. Mults of 3, this recursively defined set by this definition. So let's call this def 1. Recursively defined set, okay, by def1. So I want to show that these are one and the same set. Well, so we proceed in two steps, right? We do, how did you prove in, say, 1166 if you covered sets or some other class? How do you prove that two sets are one and the same? There are usually two steps, right? So we proceed, we show this in two steps. One, we show that every multiple of 3 belongs to the set S. So if an element is a multiple of 3, then it can be generated by the recursive definition. That's one way. And the second, the other way, is if I can generate an element according to this recursive definition, then that guy has to be a multiple of 3. That's what it means by definition for two sets to be the same, right? The two sets to be the same. Okay. First we show that let's start from here, this direction, that A is a subset of S. Show that A is a subset of S. So every multiple of 3 can be generated by the recursive, by def1, by this recursive definition. Okay, so let's show that. So this is this direction here, this guy. That's first. Okay, we prove this by, so proof of this step is by induction. Proof is by induction. Okay, now help me. So now you have like one sub piece of this theorem that we're proving, and that's proof by induction. It's standard induction. So now I can probably get your help with this because you know a lot about induction. So what's my first step in inductive proof? So first, let's be clear what it is that we're proving. We are proving that I'm repeating myself, of course, but it's okay. Every multiple of 3 can be generated by this recursive definition. Okay, so let's see. So what's my step 1 in any recursive proof? And I want to introduce some n here. So okay, proof is by induction. I've already told my reader that I'm proving this piece by induction. And I'm saying that first, writing down the first thing. Let Pn be the statement. This is the inductive hypothesis. Be the proposition or the predicate. I'm going to write proposition. A proposition that 3n is in S for, so we're taking positive integers, okay? Let's take positive integers. So 3 is in S and so on and so forth. So that's my Pn proposition. That's what we're trying to prove. Are we on the same page so far? This seems like we're taking baby steps, but that's how you proceed to be able to take giant steps later. So that's Pn is my proposition. Okay. Okay. What's my next baby step in this sub-proof of this piece? What's my next step? I've written down my inductive hypothesis. Now, what's my basis step? Why is my basis step true in this inductive proof? So why is P1 is true? Because what does P1 say? Because, yes, please.
1 times 3 belongs to the set S.
Yeah, is in S. How can I justify claiming that this is in S, that 3 is in S? Simply why?
Because 3 is a multiple of 3.
By the basis step of the definition. That's correct. But let's just write down I want to make this proof as clear as possible. So every step has to be made super clear, and about to write down every step. Because the basis step of the inductive of the recursive definition, of the step of the set S, tells me that 3 is in S. So let's write down the reason it's true, because by the basis step of definition, def1 here. We'll call this def1. The basis step simply says that 3 is there. So that's clear. And what's my next step? Inductive step. So what do I want to show? So help me out. So why is pk plus 1 true if I assume that pk is true? So we must prove, must show that pk implies pk plus 1, right? So assume pk. What does it say? That 3k is in pk. So pk is true. Here's what pk says. 3k is in S. pk plus 1 says 3k plus 1 is in S. Why can I claim that pk plus 1 is true? Has, well, you never write has to be true, but I'm going to write it down that way. Has to be true, is true, has to be true, because by the recursive step 3k plus 3, which is that, this belongs to S by the inductive hypothesis, by pk, and this belongs to S by basis step. So their sum has to be in S by the recursive step of the definition, because it's 2 elements that are already in S, and the recursive step tells me that if I have 2 elements that are in S, they must be, their sum must be in S by recursive step of definition 1. Okay, that's great. At this stage, okay, so we proved one part. So now we're proving the other way. So what we are proving now, so let's give this a different color just to make sure that we are distinguishing it. So let's go with something like green or something. Now we'll call this green. Now we're going to prove that S belongs to, so anything that the recursive step generates, this is the second piece of the proof. Now we prove, now we show that anything that the recursive step generates is in A. What do I do here? Don't use induction here. What I essentially want to claim is that anything that this definition here, anything that this definition here generates. So is it clear? Is it clear what we're doing? Like, these are completely different proofs. Now we're proving the converse of what we proved in part 1. In part 1, we said that every multiple of 3 can be generated by the recursive definition. Here, we're proving the converse. Here, we're proving that if something can be generated by the recursive definition, then it's going to be a multiple of 3. Okay, so there's no induction here. We just have to check. So, well, what's generated by S? So we check. So let's just be clear then. So let's check elements. Let's check that the elements generated by definition 1, which is on top, by def 1, by this recursive definition, are multiples of 3. Multiples of 3. But they are, well, basis step, so start here. Basis step generates just 3. Basis step, now I'm not talking induction, notice, basis step of the definition, of the recursive definition. These are 2 different things. The recursive definition, induction, closely tied, but different things. The basis step of the recursive definition tells me, right? Okay, the basis step of the definition says what? That 3 says 3 belongs to S. But 3 is good because 3 is a multiple of 3. So whatever the basis step generated, that happened to be a multiple of 3, is in A. Is, so let's write it down this way. So S, but S belongs to A. Oh, oops, what did I just write? This is silly. So, but 3 belongs to A. But 3 belongs to A. So whatever is generated by the basis step, we're done. Okay. Now, what do we need to also show? That if I have two elements that are themselves multiples of 3, then their sum is going to be a multiple of 3. But this is simple because you can rely on algebra. So this second direction of proof is actually pretty straightforward. So what we have to show here, any integer generated, any integer generated by the recursive step belongs to any integer x plus y generated by the recursive step belongs to A because we get to assume that because x is assumed to be in A, is some multiple of 3, y is assumed to be in A, some also x is, so x is like 3k and y is like 3m, then x plus y is a multiple of 3, right? It's because it's 3 times some integer, k plus m. So x plus y has to be in A, right? So x plus y belongs to A. This completes the second proof. Is this clear? This completes the second part. So conclude that S belongs to A. So finally, right now we've shown that A is in S, part 1, and S is in A by part 2. Therefore, S and A are one and the same set. This completes the proof. Quod erat demonstrandum. As they say, guys who are good at Latin, but we just simply put a square because my Latin is not that good. Okay, so square does the job. Okay, are there any questions about this?
I had a question. So
Yeah.
in part 2, where you said that basis step, we know that 3 is in S.
Mm-hmm.
Then in the later part, like just below it, you said that X is in A and Y is in A.
Okay, where are we talking about this part?
Yeah, on the bottom right.
Right. Yes. Oh, here?
Yeah, how do we know that X is in A and Y is in A?
No, we're proving. We get to assume that X is a multiple of 3. Is my voice coming through? So what we get to assume is that anything that is generated by the recursive step is going to be in S, in A. It's going to be a multiple of A. So if I already have, so I guess your question is about this. If I already have elements, these guys already generated at some previous step, already generated at some previous recursive step. So we get to assume these are elements both in S and A, really, right? And that's what simplified. This is actually simple piece if you think about it. Previous recursive step, right? This X and this Y. So if I get to assume they're already multiples of 3 that were generated on some previous recursive steps somehow, right? Then their sum is also going to be a multiple of 3. And that is true. It's, because each of them is a multiple of 3, so their sum has to be a multiple of 3. There's no other way, right? The recursive step generates a new element, but it generates a new element based on what has already been proven to be in A, right? So X and Y are both generated by S, by this definition, the definition 1, and they're also already in A. So they are multiples of 3. Okay, does that make sense? So if you think about this, spend the time it takes to think, just give it the time it needs, then it will be clear. And you should, because you'll be asked to prove something like this, maybe. This is clearly an example. Maybe it's a simple example, but a set that would be generated by some recursive function you write in some software somewhere. Okay, so how do you know that it's correct? This is an example of proving that it's correct. Well, induction can help you prove that it's correct. Well, notice the structure, however, before we leave this completely. Okay, so we're proving that whatever's generated by this recursive definition is the same as this set, which are multiples of 3. Then I have 2 sub-steps in this proof. I have step 1, I have step 2. I'm proving this direction in step 1, that anything that is a multiple of 3 must be generated by this recursive definition. Then I'm proving the other way, that anything that the recursive definition generates must be a multiple of 3. And the sub-pieces end up not to be very difficult to prove, but you get the idea of the structure, right? You just have to follow the logical structure of this in proofs. All right, does it make sense? So let's get back to trees if this makes sense. Let's talk about full binary trees. Okay, so we have a few versions of them, but here's a set of full binary trees. Okay, so what is generated by these guys? So let's just, as a reminder. So I know that this guy is a full binary tree. That's generated by the recursive step. It's just one node. That's what this guy says. Okay, it's called the root of this tree. It just has one node. That's basis step generates that. Basis step. Recursive step. So recursive step. Again, this is not talk about induction. This is recursively generated step. So recursive step generates a structure like this. In fact, one application of the first application of the recursive step generates just one element in this set that we're trying to define. Okay, so let's call this first recursive step. Then have second recursive step, second application of the recursive step. So what can be generated now according to this rule? Well, I already have a couple of trees that I've already generated, okay, by the basis step and one application of the recursive step. But this gives me a rule for generating new elements. So it says, take a new element, call this root now, and then take any of the trees that have been generated before, like this one. Okay, so this was generated on the previous step, and make that a left subtree, and make something else a right subtree. Could take a replica of this again, could take this one again, but let's take, for example, this one. Okay, apparently, okay, so this is tree 1, this is tree 2. Okay, so apparently that blue structure is also a tree. But on the second recursive step, on the second application of the recursive step, I can also generate a structure that looks like this. Okay, so, okay, this is my tree T1, T2. We called this tree, right? Remember, just call T1 stands to the left of T2. Let's just call this guy Joey or T1, T2. It doesn't matter. But this notation is convenient because it tells me that T1 is the left subtree and T2 is the right subtree. Okay, what else can be generated? This can be generated during this application of the step, but I know that this guy is already in my set. I know this guy to be there. So yeah, while this step can generate the same thing that I already have, same element that I already have in the set already of trees that I'm building up, then I leave that guy alone. But I can also generate something like this. This is a full binary tree. Okay, this is a full binary tree, and so on. Here's a full binary tree. These are the trees that can be generated during this second recursive step. And you can keep applying this recursive step as many times as it makes you happy. In fact, theoretically, an infinite number of times, and you get structures like this. Okay, okay, maybe like this, maybe like this, like this. Okay, like this. Now, that we have some idea of what these full binary trees are, we also introduce some quantities defined on those structures, on those binary trees. And those quantities are that we define the height of the binary tree. Okay. So here's the definition of a height. Okay, so let's give an example. So let's say this is a tree. Let's say a full binary tree. Let's say this is a full binary tree. Maybe I have this. Let's make it slightly taller. Okay, if you remember from last time. Okay, so this tree is generated at some step of the recursive definition. Okay, so apparently I've taken this new root and attached to it two subtrees, this guy and this guy. Okay, let's call this T1 and let's call this T2. So again, this is a new tree. This tree, this guy with this root is, according to our notation, T1, T2, right? This is according to this notation that we had previously, this guy. So I just drew one example of a tree. And now, what does this definition say? This definition says the following, that the height of this tree, and we talked about this last time a little bit, okay, so height of this tree is going to be whatever the height of T1 was, whatever the height of T1 was, well, the height of T1 is going to be 1. Whatever the height of T2 was, okay, the height of T2 is going to be 3. It's going to be 3. Take the larger of these guys, okay, which will end up being 3, and add 1 to it, which will end up being 4. So the height of this tree ends up 4, okay? Okay, so this is clear, right? How do I know the height of this guy was 1 and the height of this guy was 3? That knowledge was gained during the previous applications of the recursive step, okay? And so, for example, let's do something from the basis step. The basis step tells me the height of this tree, let's say this is T. Height of this T is 0. Then I generate some new tree during the recursive step. Okay, this one, the recursive step of the definition tells me that the height of this tree now is going to be 1 plus whatever max of T1 and T2 was. Okay, so is this clear, or am I belaboring this point? What do people say? 1 plus max of height T1 and T2. T1, T2. Okay, so do people see that the height of this tree is 1? Right, does that make sense? It's the height, the definition of the height, the recursive definition of the height is very closely tied to the structure of the tree itself, which is also recursively defined. Okay, so people get an idea what a height is. There's one more thing. Let's define, let me copy, okay, all right, let's define this. Okay, so we also want to define the number of vertices in a tree. So a vertex, so these guys are called vertices. Okay, these are rooted trees. One of these vertices is selected to be a special vertex. Okay, so the number of vertices in a tree, in a full binary tree, satisfies this relationship here. If you just have root, if you have just one tree generated the recursive step, well, that has one node. So the basis step tells me that there is only one node in the tree. And the recursive step adds one more node every time, right? So it takes one node like this and connects it to two subtrees. So n of t, let's use a different color here, then n of t, number of nodes in t, is going to be whatever the number of nodes were in T1 plus whatever number of nodes are in T2, right? In these two subtrees, plus 1, because I've just added this one root at the top. So the number of rows, so every time whenever I generate a new tree at a recursive step, I add one node to whatever number of nodes I had previously. And the number of nodes I had previously is the sum of the nodes in T1 and T2, right? So I add one node each time. Okay, so I think that's clear. Okay, so now that we have these two definitions of what nodes are, what a height is, we'd like to prove some result. And that result is going to be this. Okay. First, you're given a theorem to prove. Okay, on a homework question or quiz, exam, whatever. First, determine, does it make sense? Okay, so what does that even say? Always look at the, just as in programming, right? So you want to make sure your edge cases and boundary cases are done correctly. There's no bug in your code. Same thing here. So let's understand what this says first before we even attempt the proof. Let's take some edge cases. When can I actually have equality here? Okay, in terms of full binary, let's draw full binary. Let's draw a tree like that and see what it says. What's the height of this tree? This is a full binary tree. It's also complete. This is also called a perfect binary tree. It's full, complete, and all of its, these are called levels, by the way. Level 0, level 1, but let's not worry about those. Okay, levels. You can start leveling at 0 or 1, depending on the book you're reading. That has, maybe I'm complicating this thing, has nothing, this theorem doesn't say anything about levels. I'm just telling you, it's just levels. Okay. First of all, what's the height of this tree?
3.
Yeah, the height of this tree is 3. What is 2 to the 3 plus 1 minus 1? If I take this quantity, I have 15. Now let's count the number of nodes. Let's count the number of nodes. When you have in this in any perfect binary tree, the number of nodes. How do you get the nodes? Well, you start with one node. Then you start. Let's count. The reason I mentioned these levels is just so that we methodically add up these nodes. Then you have 2 nodes at the second level, which we called level 1. Then you have 4 nodes at this next level, which we called level 2. Notice that level corresponds to the power of 2. Okay, this is 2 to the 0, 2 to the 1, 2 to the 2. Okay, 2 to the 3. Okay, then I have 1, 2, 3, 4, 5, 6, 7, 8 nodes there. When I add these guys, and I know I'm writing it this way, but 4, 8, I should probably write 2 to the 2 to the 3. Now it's better. Okay. Okay, what's that? Isn't that 2 to the 4th minus 1? Okay. Didn't you guys prove something like this by induction earlier? This is just to see a connection. It's all these little connections in math. But anyway, the sum, if you account for these nodes level by level, you see that you have 15 nodes. Okay, the number of nodes in this, the 15 nodes, is exactly this number here in this theorem. Okay, height of the nodes plus 1 minus 1. Okay, so if you draw, every time you draw what's called a perfect binary tree, which is a full complete binary tree whose last level is completely filled, okay, perfect tree, you'll see that this relationship, this equality, in fact, holds. What this theorem says, though, is something interesting. It's more interesting than this. It says that this structures, these full binary trees that were generated by this recursive definition, and those definitions of those quantities, the height of the tree, the number of nodes, also recursive definitions, are such that you can never, you always, this inequality will be observed, basically, is what it says. So the number of nodes can never be larger than this quantity that depends on the height. Okay, so you can, so in a full binary tree, you cannot have too many nodes, basically. Okay. So by the way, does this equality, before we go on to proof, now you'll help me prove this, but how about if I didn't have a full binary tree? If I had something like this, where, you know, like maybe it wasn't full, maybe I didn't have this, then the number of nodes here, number of nodes in this tree, is going to be 13 if you count all the nodes. Well, I had 15 deleted too. That's why I know it's 13. But if you count them, it's going to be 13. That's going to be less than 2. What's the height of the tree? Has the height changed? The height of the tree is still 3, right? So it's going to be 2 to the 4th minus 1, which is still 15. So 13 is no greater than 15. That's what the theorem says. Okay. So if your tree is not perfect, then you have strict inequality. If your tree is perfect, then you have strict equality, just equality. Okay. All right. So that should make sense, at least what the theorem wants us to prove. Now we're actually going to prove it. Okay. So can I delete this? So let me make one more copy of this. Let me paste it here in case we need it later. And I'm going to erase this now that it's clear to everybody what it is that we're doing. We made some sense of what we're asked to do. And I'm going to clear this space here. How would you prove this? Okay, proof is by structural induction. Induction. Okay, what do we have? We have the basis step. What are we proving? So help me out. What is it that we're proving? The basis step. What am I proving in the basis step? So why is this true? Is this true for anything that's generated during the basis step of the definition of the full binary tree? So I have to kind of like remind myself, what was that basis step of the definition of the full binary tree again? Okay, so if I'm just learning this, I just forgot. So I'm going to go back and look at the definition again. Okay, when did we define it? Oh, okay, so then I can solve the definitions probably up there somewhere. And then I remember that the basis step of the definition tells me that only R, this R, is what was generated. That's a full binary tree. That's what was generated during this basis step. So why is this inequality true if my tree consists of a single root? Well, it's true because, so let's write it down carefully. The only tree we have, the only tree here is R, and the height, so this is my T. So the height of T, which is 0, and N of T, which is 1, we have that 1, which is N of T again, is less than or equal to the 0 plus 1 minus 1, which is 2 minus 1, which is 1. So since 1 is less than or equal 1, so this is, okay, this is going to be 2 to the height of T plus 1, right? This quantity. So this checks out. So the basis step, well, this is not the end of the proof, but the basis step checks out. Okay, so the basis step just gave me one tree, and that tree just satisfies this inequality. So we're good to go with the basis step. Inductive step. Looks like here we need to write a little bit more. So do you mind if I clear this space? By, okay, so basis step. Can we, so we have this basis step, right? So basis step works out, okay? So basis step is here. Induction. Okay, now what should I write down here? Recursive step or inductive step? Inductive step, of course. I'm sorry, recursive step, of course. Right? So what am I proving? Just help me out so we don't lose sight of where we are in the forest. So recursive step. Here's my recursive step. Assume, so at the recursive step, I'm constructing a new tree. Like this is my new tree. So let me do a little bit of scratch work first and then cleanly write that. So this is my T, which is T1, T2, right? T1, T2. And here's some subtree here, T1, and here's my other subtree, T2. Maybe T2 is taller, maybe not, whatever. But this is the tree that was generated at the recursive step. About the sub pieces, T1 and T2, we get to assume that this holds. That's the whole proof by structural induction. So we get to assume that number of nodes in T1 is going to be less than or equal than to the whatever the height of that T1 is, which I don't know, but I get to assume that the number of nodes there is at most this quantity. And the number of nodes at T2 is at most that quantity. That I get to assume, right? So now we want to prove that for this tree, the number of nodes here, the number of T, which, by the way, so what we're proving, what's my Simpson's cloud? At the end of the day, I want to prove this. This is what I need to prove, right? So how do we prove this? Well, I start here, and I want to end up here. That's my Simpson's cloud, so it's on the side. So I know that the number of nodes in my T, this is my T that was generated at this recursive step, is going to have to be 1 plus the number of nodes in T1, that by definition, so by definition of n of T. It's going to be the number of nodes in the first tree plus the number of nodes in the second tree. That's good. Now, I also know, so help me out here so that I don't get lost in the middle, that I get to assume a couple of things here about the number of nodes in the first tree and the number of nodes in the second tree. So I know that this is going to be 2 to the height of T1 minus 1. Okay, I'm sorry, plus 1. Minus 1 plus this second number of nodes there is at most whatever its height is, right? And that minus 1. So that holds by the inductive hypothesis. Okay, so by these pieces, I know that whatever is generated at the previous recursive steps, whatever I already have in this set that's being built up recursively, okay, those elements already satisfy this inequality. So that's true. Nobody argues with that, I guess, so far. Okay, so what do I do now? Okay, so now I'm kind of stuck. So I need to get here to this green piece somehow. So now this is like some kind of math question from high school or middle school or something like that. So how do I get here? So now that's like a little math puzzle. Okay, well, first of all, okay, will like canceling these ones get me anywhere? I think so. That may seem like a good idea, right? So this one, so let's write it down this way. So this is the same 2 to the height of T1 plus 1 plus 2 to the height of T2 plus 1. This plus 1 cancels with one of those minus 1s, and I have a minus 1 here. That's a good start. So I already isolated minus 1. Now I want to show, so why did I do this? All right, first of all, do people see this, that I just didn't do anything, really, except I canceled once? Now notice what I'm trying to show here. I want to get to this green piece. And am I stuck or am I not really stuck? Well, can I say something about this sum of these powers of 2? Well, I have 2 of those. Can I say that this is going to be less than or equal than twice, whatever the largest of the 2 pieces is? Let's say this is like, let's say this number is like 1024 and this number is 512 or something. I don't know. These are both some powers of 2. I don't know. These can be in the gazillions. But their sum is going to be at most twice whatever the larger of the 2 is, right? I can say that. Max of the 2 of these 1024 or 512. So, whatever these guys are, max of those, I can certainly say that. And then I carry this minus 1 over. This is a bit of algebra, but do people agree with me in this step? right? Okay, so let me erase this tree. Okay, so now what do I do here? Somehow I want to get to this green piece. Again, this I'm like inside a puzzle a little bit here. Okay, that was like a good start. Can I further simplify here what's inside here? Actually, do I need the -1s in there? If I have this as like, if this is something like max of 1024 -1, and like 512 -1, like 2 powers of 2 -1s, right? Do these -1s matter at all? Do these powers? I can just as easily write this as 2, whatever the max of these two is. Oh, actually, it should be less than or equal, of course, but can I write it down this way? 2 to the, just get rid of these pesky -1s there. 2 to the, and I carry over this -1 here, of course. Do people agree with that? Okay. All right, fine. This is a good start. What else can I say? Can I further simplify this? Again, notice that I still have my goal in mind. My Simpsons cloud is still here. Here's my Simpsons cloud. This is what I'm trying to get. I have my -1 is right here. That guy is pretty good. Trying to get, to make out of this somehow the total height of the tree. Can I say that this is the same? Can I say that this is the same as 2 to whatever the larger of the exponents is? Can I say that? Do people agree? Let's agree. Okay, so think if just to be clear, think of this in concrete terms. Some power of 2. Okay, again, it's let's say this is 1024, and this is, let's say, 512. This is going to be, okay. So then we're talking about something here. This is scratch work. So I'm speaking. This piece is saying that this is max of 2 to the 10 and 2 to the 9, right? So the answer, of course, you know what the answer is. The answer is 2 to the 10. But I rewrote this as I'm saying that this is the same as 2 to the max of 10 or 9, which is, well, the max was 2 to the 10 here. You knew that. But it's the same way of writing this. Well, what is max of 10 and 9? This is 2 to the 10 anyway, and these two are equal. Right? Does that scratch work make sense to people?
I have a question.
Yes, please.
One from the previous, you just disappeared -1 and +1.
This one?
Yeah, the +1 and the +1 in the exponent, and the -1 below. It just.
Let me see what the
H of T1 +1 in the exponent, that also disappeared. The +1.
Oh, yeah. So yeah, we just okay. So you're saying, so let's okay. This green piece is clear, right? This green piece is clear. Here's another. Let's call this a blue piece. So you're saying, why is it the case that 2 to the, let's call this 8. Okay, all right. You're saying, why is it the case that max of these guys? You're saying, why is it the case that max of these guys is max of 2 to the, this guy, let's say, let's do it step by step, 2 to the second tree's height. Is that what you're saying? Why can I subtract those ones? Did I get your question correctly?
Yeah, and you also removed the one from the.
Yes. Okay, let's do it a step at a time. Do you agree with this step? So here I have something like max of 2 to the 10th -1, 2 to the 9th -1. Isn't it at most max of 2 to the 10th? 2 to the 9th? Do you agree with this step? And then I'll talk about removing that 1 in the exponent too. Do you agree with this?
Yep.
Agreed? We all agreed? Okay, then let me remove that green explanation. Now, if we agree with this piece, then my claim is that this is also smaller than 2 to the ht1, 2 to the ht2. Okay, so again, let's write in green why that would be the case. So here I have 2 to the, I don't know, well, let's say 20 plus 1, 2 to the 17 plus 1. So if I write something like max of these two numbers, which is this guy, isn't this true that it's smaller than max of 2 to the 20? So this is 21. This is 22. I'm sorry, this is 18. So if I subtract 1 from both, can I just get, isn't this true? Is that true? Oh, no, hold on. This is not true. What am I saying? What am I saying? You're absolutely correct. I was about to lie to you. I should add a 1 here. Sorry about that. I should add a 1 here. Okay, sorry about that. Okay, do you agree then? Okay, continuing here. I'm glad you asked because I was about to lie to you. How should I write this? Okay, so not this, but I want to write here max of 2 to the whatever max of HT1 and HT2 is plus 1. Okay, so what would that be in green? Now I'm running out of, we can add, release to add a page, great. So notice in green, what am I doing here? So I had this max. My claim is that this is not true. This is I was about to lie to you. What I'm writing here is that this is smaller than this. What I just wrote here. This is smaller than 2 to the max of 20 or 17 plus 1, which is the same as 20 to the 20 plus 1, which is 2 to the 21, which was the answer to begin with. Do people see the logical connection here, the chain? Why that was the case? I'm so glad you asked me because I was about to lie in the proof. But anyway, so are we on the same page? Still, so this is our main, this red here is our main, main logical chain. The rest, the green ones and the blue ones are the justifications of the steps, just to be clear. Okay, so now let me erase this part and we're done. Okay, so we just need to say one more thing here. We're just one step away. So what do we need to do now? Okay, so now if you agree with this step, I actually had it correct here. Did I add this one later after you found the mistake? Okay, so anyway, so what do I have at the top? Of course I needed this plus 1. What do I have? This is what? This is 2 times the height of the tree itself, right? Minus 1. This by definition is the height of the tree. But this algebraically is 2 to the, to h of t plus 1. 2 to the ht plus 1. And this minus 1 I'm carrying over. Now, we're in good shape because this guy is in my Simpsons cloud right there. This is what we wanted to prove. This is what we were after. We needed a few steps here. And of course, the steps need to be justified, but we certainly got there. This is that which needed to be demonstrated. This is our quod erat demonstrandum. Okay, this is our QED is falling out here from here, but this is our QED. Okay, are we all on the same page? This is a nice proof. I mean, it involved a few steps, but this is how you carry out proofs by structural induction. These are recursively generated structures, and then you have these things, needs to be proven about that structure, about those full trees, that the number of nodes in a full binary tree can be at most this quantity that depends on its height. It can't be anything, it can't be bigger. And this is a nice proof of it. Okay, so any questions?